Hello everybody and welcome to the final episode of this series of the big questions made little. Today I'm going to be talking about the last three elementary particles, W+, W-, and Z bosons, or Z bosons if you live in America or Canada or somewhere else. See if you can guess where I live based on my accent, but I'm going to be referring to it as the Z bosons because that's how I say the alphabet. Moving onwards. So these bosons are obviously bosons, as I just said. Bosons are one of the three types of elementary particles. However, unlike the other two types of elementary particles, bosons kinda don't have mass properly. It's a little confusing. They're more waves than actual particles, although they behave like both simultaneously. It's a little confusing, but they're what's known as force-carrying particles. For example, the photon carries the electromagnetic force. It's the particle that force works through. For example, electromagnetic wave is a wave of photon particles, although they're also waves in of themselves. But they're what's called energy particles. They behave like bits of energy, and they behave like matter particles at the same time. Sometimes it gets confusing. Anyway, these three particles, the W+, W-, and Z bosons, are together known as the weak or intermediate vector bosons. They basically are the force carriers for the weak interaction, or the weak nuclear force. This is one of the four fundamental forces. It's the last one that I haven't actually covered yet. Just to go over it one more time, the electromagnetic force is mediated or carried by the photon. The strong nuclear force is carried by the gluon. The Higgs field is it's another one. It's more of a theorized force, but that's controlled by the Higgs boson, and the W+, W-, and Z bosons control the weak interaction, or the weak nuclear force. Now, the final of the fundamental forces, the four that we definitely know of, are of course electromagnetism, the weak and strong nuclear forces, and gravity or gravitation. Now, the particle that is responsible for the gravity force or gravitation is called the graviton. It's very original, isn't it? This is a theorized particle. It's not one we've ever actually found or has actually proven really exists. And there are some theories that the graviton is actually two gluons that are bound together. That's an interesting one. Feel free to mull over that yourself if you like. I may well go back and look into it in more detail in another video. But today I'm talking specifically about the W and Z bosons, so let me get back to the point. The W boson is the only one to have a real antiparticle, because they are energy particles, if that makes sense. They're little blobs of energy and matter. It's slightly confusing. Because matter particles are made out of energy, it's in almost like a different state. It's difficult to describe because it doesn't make sense in terms of laws of physics on the macroscopic level. It's not the same as the difference between water and ice. Anyway, because matter particles are formed from energy, in order to get them, what usually happens, as we understand it, you get two, matter particle and an antimatter particle, and if they hit each other again, they both convert back into energy and start producing gamma waves, which are photons, electromagnetic waves, with really high frequencies. They're very powerful energy waves. But because bosons are almost energy particles, that sentence doesn't really make sense, but I think you can understand what I'm trying to say. They don't really have antiparticles, but the W bosons do. The W+ boson and the W- boson, neither of them are matter or antimatter, but they are each other's antiparticles. And the Z boson is its own antiparticle, and it's completely electrically neutral. The spin part, these three particles, because of course they're bosons, will have a spin of 1. And while the W plus and W minus bosons have a magnetic moment, which is something to do with forces, which I believe Rocky has explained at some point in one of his past videos. Feel free to check that out. But the Z bosons don't. But all three of these particles are very short-lived. They have a half-life each of about 3 times 10 to the minus 25, or that number appearing on your screen, seconds, which is really small. But a half-life does not necessarily mean how long the particle will exist. If you have, for example, it's usually used in terms of radiation. So if you have, for example, a kilogram of uranium, because it's a radioactive substance, it has a half-life. Okay, so if you've got, I can't remember, I don't know off the top of my head what the half-life of any specific isotope or form of uranium is, so I'm just going to use the one of uranium-238, which is the most common isotope of uranium. And has a half-life of about 4.5 billion years, or the age of the Earth. But what that means is that after this amount of time has passed, half of the atoms in that substance will have altered, they will have radiated and become changed into a more stable substance, either through alpha, beta, or gamma radiation, and they will have changed into a different type of atom. I will explain in the future how that works, how that happens. However, after this 4.5 billion years has passed, although you still have the same mass, half of it is no longer that isotope of uranium. It usually becomes a different element altogether, but half of it is no longer that uranium. Half of it is. After another 4.5 billion years, however, you'd expect for there to be no uranium left, but there's not. It's a probability, which means that no matter what mass of uranium you have, after 4.5 billion years time, half of the atoms in that sample of uranium will have radiated and no longer be uranium. And then the same will happen again. In another 9 billion years time, you'll have a quarter. The mass of specifically uranium atoms will be a quarter of before, then 8th, 16th, 32th, 64th, etc. I'm not going to start listing off the powers of 2 though. Anyway, if you want to know a bit more about where their names came from, the W bosons came from the weak force. Weak, of course, done with W, because those were the first that were discovered. Then they named the Z boson afterwards from the 0 electric charge that it has, realizing that they still had to have this third particle for the weak interaction to be fully proven and working the way it does. That's all I've really got to say to you about these 3 last particles. This is the last video I'm putting out for now. I will be back at some point in September. Rocky will be returning to you sometime in April or May. But until then, you will have Geekman and Danny Astronomy Man still putting on their videos in the meantime. But this is my 6th episode of this series, my 9th episode altogether. So this has been going a while. But when I come back in September, I'm going to be doing a far more different approach to the way I make these videos and the kind of thing I talk about, something a bit more interesting than these kinds of particles. Until then, though, thank you very much for watching, and I hope to see you all later. Bye.